Welcome back to The Explainer. Today we're tackling something that sounds, well, impossible. How can you take two moving waves, smash them together, and get one that stands perfectly still?
I know, right? How is that even possible? Well, to get to the bottom of it, we first have to ask a more basic question. What happens when any two waves meet?
So here's the plan. We'll start with what happens when waves collide, then figure out how to make them stand still. After that, we'll look at some real-world examples, crunch some numbers, and then you'll get a chance to test what you've learned. Sound good? Let's jump in.
Okay, so what does happen when two waves cross paths? You might imagine them bouncing off each other, kind of like billiard balls, but the reality is actually way simpler, and it's all down to this one fundamental idea in physics.
It's called the principle of superposition, and it's basically just addition. When waves meet at a single point, you just add their displacements together. If one wave is up by 5 units and the other is up by 3, the new wave is up by 8. Simple as that. Now, this simple idea of just adding them up leads to two really cool and totally opposite outcomes. If the waves are perfectly in sync, what we call in phase, their peaks and troughs line up and boom, you get a much bigger wave. That's constructive interference. But if they're perfectly out of sync, the peak of one hits the trough of the other, they can completely wipe each other out, and that's destructive interference. Okay, so we know waves can add up or cancel out. But how do we use that to make a wave that literally stands still?
Right, so here's the secret. A stationary wave isn't some magical new kind of wave. Nope, it's just an illusion, an effect that happens when you get the conditions just right. You need two waves, they have to be identical, same frequency, same amplitude, and they have to be moving in opposite directions. When they overlap, you get this amazing standing pattern.
And you know, the easiest way to make this happen in the real world is with a reflection. Think about it. A wave travels down a guitar string, right? It gets to the end, hits that fixed point, and bounces back. And just like that, you have your two identical waves, the original and its reflection, moving right through each other. The perfect setups for superposition.
And check this out. This shows exactly what's happening. You can see the incident wave and the reflected wave passing through each other. But look at the purple line, the result of them adding up. It's not traveling anywhere. It's just oscillating up and down, completely locked in place. That's our stationary wave. And see those points where the purple wave isn't moving at all? Those are called nodes. At these exact spots, the two waves are always perfectly canceling each other out. The string, or whatever the medium is completely still right there. Then you've got the opposite, the points of maximum wiggle. These are the antinodes. They're right between the nodes, and that's where the two waves are always adding up constructively, giving you the biggest possible vibration. So this brings us to a really, really important difference. A normal wave, what we call a progressive wave, is all about transferring energy. Think of a ripple in a pond. It carries energy from the splash outwards. But a stationary wave, it doesn't transfer energy at all. The energy is just trapped. It's stored in those oscillations, vibrating in place, but never actually going anywhere. Okay, so this might seem like a niche little physics trick, but I promise you, these standing waves are everywhere. Let's go find some. You've definitely heard them. Every time you pluck a guitar string or draw a bow across a violin, you're creating stationary waves. Each specific pattern, or harmonic, corresponds to a different musical note. That beautiful, simple one-loop pattern, that's your fundamental frequency. The two-loop pattern, that's the next harmonic up. And it's not just strings. Sound waves do it too. This experiment is just awesome. They've put a fine powder inside a tube and are playing a sound. See how the powder forms these neat little piles? It's being pushed away from the vibrating antinodes and settling in the calm, still nodes. It literally makes an invisible sound wave visible. You can even find these waves just by listening. Ever blown across the top of a bottle and changed the water level to get different notes? That's what's happening here. When the length of the air column is just right, you hit resonance and the sound gets super loud. That's because you've created a perfect standing wave with an antinode right at the opening. And it even works for waves you can't see, like microwaves. You just send out a microwave beam, reflect it off a metal plate, and you've created a standing microwave. Then you can use a little probe to move through it. You'll find spots with almost no signal, those are the nodes, and spots with a max signal at the antinodes. It's a super simple way to measure the wavelength of something you can't even see. All right, that's enough theory for now. Let's get our hands dirty and actually put some of this physics to work. Time for a little math. Okay, here's the problem we're going to tackle. We've got a string, it's 75 centimeters long, we're vibrating it at 15 hertz, and that creates a nice pattern with 3 loops. The question is, how fast are the waves traveling on that string? Okay, first things first, let's picture what's going on. We have a string, and it's vibrating in 3 distinct loops. Now, the most important thing to remember here is that each one of those loops is exactly 1/2 of a full wavelength. So, the trick is to relate the physical length of the string, L, to the wavelength of the wave, lambda. If we have 3 loops and each loop is half a wavelength, then the total length L must be equal to 3 times lambda over 2. So we just rearrange that little formula to solve for the wavelength. We plug in our length, remember to convert 75 centimeters to 0.75 meters, and out pops a wavelength of 1/2 meter. Awesome. Now we have the wavelength, and the problem already gave us the frequency. And whenever you have wavelength and frequency and you need speed, there's one magic formula you turn to, the wave equation. Speed equals frequency times wavelength. It's one of the most fundamental equations in all of physics. So we just plug in our numbers, 15 hertz for the frequency times the 0.5 meters we just calculated for the wavelength, and we get our answer. The speed of the waves on that string is 7.5 meters per second. Done. All right, you're getting the hang of this. Let's do a couple more quick problems just to make sure these ideas really stick. Okay, question 4. We've got a string where the waves travel at 48 meters per second, and the frequency is 64 hertz. It's asking for the separation between successive nodes, so the distance from one node to the very next one. And here's the key thing to remember. The distance between 2 nodes is always half a wavelength. So step 1, use the wave speed and frequency to find the full wavelength. That comes out to 0.75 meters. Step 2, just divide that by 2. The distance between nodes is 0.375 meters. All right, next one. Imagine an empty bottle that's 25 centimeters deep. What's its fundamental frequency? This is a classic pipe closed at one end problem because you have the open top and the closed bottom. Now, for a pipe that's closed at one end, the simplest standing wave you can make, the fundamental, is a little different. You have to have a node at the bottom and an antinode at the open top. That shape fits exactly 1/4 of a wavelength into the length of the bottle. So you use that to find the wavelength, which is 4 times the length, or 1 meter. Then use the wave equation again to find the frequency, which comes out to 340 hertz. Okay, last one, and this time we're going to work backwards. The question says the first harmonic on a string has a wavelength of 2 meters. So how long is the string? This one's actually pretty simple if you remember the basics. The first harmonic is that one single loop. And how much of a wave fits in one loop? Exactly half a wavelength. So if the full wavelength is 2 meters, the string's length must be half of that. The string is 1 meter long. Easy. So let's recap the whole journey. We started with superposition, the simple idea that waves just add up. We saw how that leads to stationary waves when 2 identical waves travel in opposite directions. And this creates that amazing pattern of still nodes and vibrating antinodes. And most importantly, we saw that this isn't just some textbook curiosity, it's the reason music works. And it's a tool we can use to measure things we can't even see. But that leaves us with one last kind of mind-bending question. If a stationary wave doesn't transfer energy, where does all the energy from the 2 original waves actually go? Well, it's trapped. It's held right there in the wave, constantly sloshing back and forth between kinetic energy, the energy of motion at the antinodes, and potential energy, when the string is stretched at its peaks. It's a perfect self-contained resonant system, holding energy in one place. Pretty incredible, right?